So, we have looked already into the basic formulation of combinational logic, right, how to represent truth tables, right, and also the various ways, canonical ways to represent the truth table into either sum of the products form or the product of sum form. We also know how to minimize such expressions using basic Boolean algebra axioms, and we also know that we would be teaching you some formal methods of minimizing such expressions. One of them is called K maps, that is what we are going to cover after we finish some of the common combinational logic blocks. So, in this lecture the focus is going to be on some of the common combinational logic blocks that we are going to come across. Okay. So, let us see that this common combinational logic blocks, as I called them or like to call them as the Lego blocks, or Lego, you want to build something bigger using these Lego blocks, right, or these are individual bricks kind of thing, right. So, once you want to build a house of a given shape, you do not want to go and start by building a brick itself, right. You basically want to use some ready made items like a brick or a concrete slab and things like that in order to build your house or build a specific room of a specific shape. Similarly, whenever you want to design a certain circuit, you do not have to start designing the circuit from the gate level, but you can actually build the circuit based on some common or higher layer of building abstractions. For example, you want to build one of the common building blocks inside a CPU or a central processing unit is an adder, right. So, instead of going to design an adder, you can simply borrow the fact that you need an adder, and that adder is a common computational common combinational logic block, right. So, similarly, there are many such functionalities that might be expected, right, that is kind of expected to be available ready made, right. So, combinational logic is often grouped into larger building blocks to build more complex systems. Okay. So, the eventual circuit that you are planning to design or you are going to build might not be combinational block itself, right. It could have a mix of sequential logic elements as well as combinational logic elements, the bigger system that you are going to design, but you need to identify the building blocks, and some of the common building blocks we are going to discuss. So, typically tens to hundreds of transistors, right, often called MSI or medium scale integration. We are going to create some circuits out of them. Okay. So, this hides the unnecessary gate level details, and it will be better for a designer to emphasize the function of the building block rather than how the building block is actually implemented. Okay. So, I will go back to the adder example. So, adder is a hardware logic block or a combinational logic block that adds two n bit numbers, right, and that n bit could be either 2 or 3 or 4 depending on what kind of adder you are considering. So, in this example or in this context, I can write this as a combinational logic black box, right. So, this is an adder, and this adder is probably, here we can write a 4 bit adder, right. So, there are 4, this is a 4 input of the first number that we want to add, and these are the next number that we want to add. So, let us call them as A and B, and A and B are going to individually have these bits, right, A0, A1, A2, A3. Similarly, it is going to have B0, B1, B2 and B3, right. Often you need an input carry, but you can just assume that there is nothing as an input carry. You simply want to add them, and then you want to give out the result. The result is also going to be 4 bits, right, and let us say this is sum. So, sum we want to represent as S, and S0, S1, S2 and S3 are the 4 bits, and then you can always have, you may have an overflow or a carry. We are all used to addition, sometimes in the last place, right, once you start adding those two numbers, there could be a overhead carry, right, and that carry is going to be an output also. So, somebody is going to design this adder very efficiently, okay, and there could be multiple options in which you can design this adder, right, but you need to like the reason we want this ready-made modules is that without going into the deep complexity or the unnecessary get level details, you can emphasize on the functionality of the block. So, suppose you have one more block, let us say this is a block block, this is some block, right. The block outputs A and B, right, the result is computed and the sum goes to some other block, right, some block 2, right. They could be combinational, they could be sequential, that is not the matter of interest right now, but what we want is that the one block outputs A and B, another block takes the sum of it. So, the right combinational logic you want to put here is an adder, okay. So, in this way you have to start identifying various kinds of such functionalities that might be commonly used, right. So, whenever we cook, right, there are some common set of spices, some may use turmeric powder, some may use coriander powder, some may use chili powder, some may use like salt, right, pepper and so on. These are like common things you do not want to, or maybe there are some higher more complicated spices, right, that is a mixture of some of these spices, right. So, all you need to know that you need to use that spice for this kind of a taste, okay. So, without going into the details of how that particular spice is made or how that particular circuit is made, that is not the not required, right. So, some of the combinational building blocks that we are going to look at are these are the names that we are going to go through, and we will look into some of these things right now, and there may be some other building blocks that may come up later. So, initially we will introduce you to this few circuits. One is a comparator. Comparator is a circuit that is going to, from the name you can understand that it is going to compare let us say two numbers, right, and there can be multiple ways you may want the output, how it is going to look like. So, a comparator, let us go through them one by one and why they are kind of very important. Comparator, what do you typically do in a comparator? You compare two numbers, right. So, one number could be x and the other number could be y, right. So, either you can say that I want to test if x is greater than y, right. The other possibility could be if x is less than y, right, and the other possibility could be x is equal to y, right. So, typically these will be the possibilities. But if you only have a single output of the comparator, you cannot represent 3 different outputs or 3 different states. With one bit you can only talk about 2 different states. So, some comparators will simplify this particular expression, and then they are going to say that if x, let us say, greater than equal to y, right, you output something, else if x is lesser than y. So, this is the other condition. This is one way you can implement a comparator, right. The other way you can implement a comparator is this: if x equal to y, then you say, and if x is not equal to y, you say another thing, right. So, this is like 0, this is 1, again this is 0, this is 1, or vice versa. So, this is how first you want to set up your set up your mind, how you want to design the circuit, what are your expected inputs, what are your expected outputs, and so on. And you always need a comparator to be supported in hardware. You write all these conditional statements, right. If you write if x is greater than y, do this, if x is less than y, do this, right. If you think of how this entire program, when it actually goes to the bare bone hardware level, this is a question of actually comparing two numbers, right, and often you are going to have hardware support for doing this comparison, right, typically known as this comparator. Okay. Then we have these things called encoders and decoders, right. We will come to again details of what these encoders and decoders are. So, typically if you have n bits, right, if there are n bits, they can represent how many possible combinations, right, because n bit number could be used to represent 2 to the power n different entities. Okay. So, you can either take this n bits, right, and try to select one of the 2 to the power n different entities, right, that is one possibility. So, you can take this n bit number and try to see which one of these 2 to the power n needs to be selected. So, there are 2 to the power n different entries, and you can do one of these things. The other thing is that you can actually select one of these 2 to the power n entries, right, and try to find out the bit combination that is going to produce that, right. So, this is like the reverse process, and this is known as decoding and encoding, right. So, we are going to look into how these things can be implemented. But if you think of applications, right, because you need to have a motivation about where these kind of functionalities need to be used in order to kind of synthesize them, or in order to know more about them or design them. For example, in a comparator, I told you we often come across loops where you want to do these comparisons and equality checks and so on. In case of in particular, let us say if you have this n bit number, you might want to choose one of these 2 to the power n different entities. One classical use case is addressing some memory location, right. So, if there are let us say 1024 memory locations that could be represented by 10 bits, right. So, these are memory locations. I will write memory locations. So, there could be one particular this thing could be 1 byte, let us say. So, I have 1 kilobyte of memory. Okay. So, you have 1024 bytes, and if you want to select one particular memory location, because you need to read the data. So, we often say we want to actually initialize pointers, and we want to read from that particular pointer, we want to write and all these things, right. For doing this thing, you need to kind of refer a particular cell here, right. So, suppose you want to read from this blue cell, right. So, this is going to have a certain address. So, what the circuit will do, it will take your n bit address, right. This is your n bit address, which is going to be a 10 bit address, because you are going to have 1024 different possibilities, which is 2 to the power 10, which is equal to 1024. So, with this n bit address, you can actually select any one of these things, right, and given a particular n bit address or a particular 10 bit address, it can be used to choose this, right. So, how does this circuit work? Because these are an extremely common requirement within a processor whenever it is executing code or writing to memory or reading from memory and so on. Okay. So, we will come across foo ladders, right. Foo ladders is an example that I have been I spoke about it many times. Comparators, decoders. There is this concept of multiplexers often, where there are many input signals, right, and you want to kind of choose one of them based on some conditions, right. So, there could be situations where you have this device and you have certain number of inputs, right, and let us say this is input 1, this is input 2, this is input 3 and there is input 4, right, and there is some kind of an output. You want to take a certain input and pass it on to the output. So, either, so suppose you want to take I3, right, and pass it on to output. So, you need to give some kind of a selection. You want to select some inputs and so that you can put it to your output. Think of a very quick analogy that I can give you is, think of this as your television set top box, right. So, you have all these different channels, right, which are coming in the television channels that comes into your set top box, and you want to select one particular channel that you want to view, right, and you make that selection and that is what is kind of fed into the output. Okay. Similarly, here, right, if you choose 1, this will be fed into it, right. If you choose 2, it will be fed, right. If you choose 4, this is going to be fed and so on, right. So, the selection is going to happen based on the condition is going to be based on how many inputs you are going to have that you need to handle, right. And also you can do the other way around, you can always take one input, right, and kind of distribute it based on some kind of a selection where you want to put the output, right. So, these are like multiplexers, demultiplexers kind of circuits that are very, very useful in designing computer hardware. Okay. I am not going to discuss programmable logic arrays, that is something which we are going to very briefly look at, we are not going to go into details, but this is something that you can have a programmable hardware, right. So, sometimes we talk about hardware that has already been developed or built or manufactured, and you cannot really change the hardware, right, because once you are synthesize the hardware, that is it, right. So, you cannot really go back and change that in any form. So, sometimes the development cycle becomes slower because once you design a circuit, you want to build the circuit and test it out and so on, and you have to make some changes and then remanufacture it, right. So, that becomes more of a difficult procedure, right. So, sometimes we have this flexibility of using programmable hardware that can emulate any kind of circuit of your choice, right. So, this is as if I would say programmable hardware logic. So, it is not a comparator, not a decoder, not a multiplexer, not a full adder, but it can become any one of them, right. So, you need to suitably program them and in order to implement anything of your choice. Even you can actually implement entire central processing unit using this PLAs, or you will learn about FPGAs and so on. You can do that entire thing just by programming the hardware. Okay. So, do not think that that particular hardware is a computer and you can program it, it is not like that. You can always have a software that will take your program and synthesize the corresponding hardware on that PLA, right. So, this is something that is reconfigurable. So, this is reconfigurable. So, if you write the right software, it can synthesize a given kind of a CPU, right, and next moment it can actually become some other thing, right, some other completely different kind of a computer hardware. It need not be definitely, it need not be a CPU all the time, right. So, you can reconfigure things and what is the kind of the soft limit. As you can see, this logic arrays, they actually set some kind of a limit on the number of gates. Okay. So, this is some hard limit, right, because if you have 100 gates, you can only realize a few kind of combinational circuits, right. Let us say you can have NAND gates, because those are universal gates or NOR gates instead of just AND and OR. But suppose you have 100 NAND gates, you can only have a finite collection of circuits that could be realized. In comparison to that, if you have 1,000,000 gates, right, you can design a lot more varieties of circuits or more complicated circuits. Okay. So, programmable logic arrays are going to also tell you that what is the capacity, how many logic elements are they going to have, programmable logic elements they are going to have. Okay. So, let us start with this equality comparator, right, using this function called XOR. So, let us first look at the truth table. Okay. So, here we are trying to somewhat look at a 1-bit equality comparator. Okay. So, you are given x and y, you need to basically tell me whether x and y are equal or not. Okay. So, often we call it the XOR function, and this could be given by x y complement plus x complement y. So, you can see how. So, very simple. So, this is the XOR function, and if x and y are equal, in this particular case you are getting 0. So, if they are equal, you are going to give out a 0, if they are unequal, you are going to give out a 1. So, that is the agreement, right, that is how you define these things. Okay. So, if 0 and 1, if you see in the second case, they are unequal, it is going to give out a 1. Similarly, they are going to give out a 1. So, in these two cases, x is not equal to y, x is not equal to y. In these two cases, x equal to y, and in this case also x equal to y. Okay. And x NOR is the exact complement of that, it is x XOR y, the complement of this entire thing. Okay. So, you can see that this is just exactly the opposite. So, in this case x is equal to y, but this has to be 1. So, this is 0, this is 1, this is 1, this is 0, this is 1, this is 0, this is 0, this is 1. So, this is the exact opposite of XOR, right. This is also called XNOR. Okay. And if you try to look at the Boolean expression for XOR, it is very simple. All you need to do is that you choose, if you look at the sum of products, for example, you choose the rows that are going to have 1s, right, and look at the mean terms. So, what is the mean term for this particular row? The mean term is going to be x complement y, right, and what is going to be the mean term for this? This will be x y complement, and you have to put a plus sign. Okay. So, you can see this is the same thing. Okay. So, it is like they say it is similar to OR gate, except that when both the inputs are 1. So, that is called exclusive OR. Okay. Exclusive OR is XOR. So, if you see in case of an OR gate, if I write the truth table for an OR gate, 0 0 is going to be 0, 0 1 is going to be 1, 1 0 is going to be 1, 1 1 is also going to be 1. So, all the terms are similar to OR, right, except this one, and in this case if both of them are 1, we typically use for OR function, right, we assign the OR value to be 1, right. Logically also it is the same, because either x or y is true. Even if both x and y are true, the expression resulting from the OR expression is still true. Whereas in case of the XOR function, if both of them are simultaneously true, we take this as a false thing, right. So, we call it an exclusive OR. It is similar to an OR gate, except when both the inputs are 1. Okay. So, this is very easy or kind of very important for doing comparisons as well as error checking, because it gives you to match two numbers. In hardware, often you come up with in various kind of scenarios, you need to build hardware where you need error checking, right. So, when you will learn more about networks, in a network a packet is transmitted, and that packet, when it goes through the network, certain bits might be flipped, right. For example, let us say this is a sender that sends out this packet 1 1 0 1 1 0 1 1, right. So, there are 8 bits in this packet. So, this is a network packet. So, what happens is this particular packet goes out in the internet, and there are like so much noise is around that, right. So, you can have bit flips and so on, and when it reaches the receiver, it might actually change, right. So, this is the receiver. Okay. So, let us say the packet has been flipped in some location, let us say let us this 2, right. Let us say these 2 bits have been flipped, right. So, what is the resulting bit or the packet that has been received? 1 1, instead of 0 1 0 is going to be flipped to 1, and next is going to be flipped to 0, then 1 0 1 1 is going to remain as usual, right. So, this you can understand, this is the flipped thing. Okay. So, now if you let us say knew what the sender is typically going to send, and whenever you receive it, you can do an error comparison. Okay. Or you can, the sender can send the second time, and you can see that whether the same thing has been received or not, right. So, depending on the application, you can come up with a scenario, but in the context of our discussion, you can take these 2 numbers, let us say the sender number, let me change the ink color, let us say the sender packet contents, which is going to be 1 1 0 1 1 0 1 1, right, and for the receiver it is going to be 1 1 1 0 1 0 1 1. So, if you try to do an XOR, right, let us say you do an XOR, you have to do a bitwise XOR, right. So, you can see that there is a 1 and 1, right. So, if you look at the truth table, 1 and 1 is going to give you 0, right. This is nothing but equality comparison. So, 1 and 1 they are equal. So, this is going to be 0, 1 and 1 they are equal, this is going to be 0, 0 and 1 they are not equal, right. So, an XOR is going to return 1, 1 and 0 they are not equal, XOR is going to return 1, 1 and 1 is again 0, 0 and 0 is 0, 1 and 1 is 0, 0. So, if you now look at this particular expression, or is this particular value, you can see that out of this 8 bits you have 2 ones, right. So, these are the 2 error locations. Okay, just gave you a very simple example to understand that okay, XOR is a very important function. It could be used for some kind of a pattern matching, comparison, equality checks, error checking and so on. Okay.